So good morning, good afternoon, and good evening in these strange times. I was looking forward to meeting everybody's small children and cats, so please turn on your video at some point during this meeting. So you are all here because, oh, and also I turned off my Slack so it doesn't interrupt. So if you have questions, if the moderators need to get in touch with me in any way, please do so verbally. Okay, so you folks are here because you have some experience in processing the data coming off of wide field imagers. We've come a long way since the invention of the CCD, and some algorithmic components for extracting information from these images has been unchanged really for many years. So for example, and this is because they are somewhat optimal in nature. So for example, extracting flux measurements from point sources in isolated point sources in high galactic latitude. Other components, other algorithmic components have seen a lot of rapid development in recent history, and this is because we are being more ambitious. As we expect imaging from half the sky down to 27th magnitude, we are no longer going to be systematically limited. We're no longer going to be statistically limited, but systematically limited. And components that we thought were straightforward, like flat fielding, for example, turns out are really challenging when you want to get down to millimag photometry. So we've identified a number of algorithmic components of the pipelines that are still challenging. And before we go into the individual talks about those components, I would like to give a high-level overview of the pipelines to give you some context of where these algorithmic components fit in and what we're trying to accomplish here. So what are we trying to accomplish here? We are trying to best combine the multi-epoch imaging taken in a variety of atmospheric conditions to extract the maximum amount of information. And we're going to do this through software. The inputs are going to be raw images, observatory metadata, calibration data, and the outputs are going to be a variety of data products. And don't pay attention to the names of these data products yet. We're going to go into these in gory detail. But note that there are two major types of data products. We will be releasing images and catalogs. While we expect that the vast majority of science will be possible with catalogs, we know that you will invent new science that cannot be done with the catalogs alone. In fact, I would see it as a major success if scientists were running novel algorithms on our images 10 years from now, 20 years from now. Therefore, the images are first-class data products that you can use to detect and measure your ultra-diffuse galaxies or test your Planet 14 hypothesis using shift and stack algorithms. While we are not so bold as to assume that we can predict all science that can ever be done with our telescope for the rest of humanity, we are so bold as to say that you should not have to redo instrument signature removal. And for the very bold, even bolder yet, that you shouldn't have to model your own PSFs or do point source photometry in high galactic latitudes. We are closest to the instrument, and during commissioning, if resources get tough, we will focus our efforts on instrument signature removal, and we commit to doing it better than you can. There's another category of, we can also split out the images into two other categories. So how we can get those data products to you, which is both fast and slow. The fast data products are going to be through our prompt processing. You'll hear me refer to this as the alert production pipeline, or AP. The other way is through our annual data release production. You will hear me refer to this as DRP. After this talk, you will not hear us distinguish between AP and DRP very clearly. And this is because the DRP and AP pipelines are constructed from the same algorithmic components. Hang on, I'm going to turn off my, the same algorithmic components. And so for this talk, I'm going to introduce how these building blocks are put together. But this meeting is really about the meat of these blocks, the guts of them. Okay, how will we know how well it works? First, you're going to hear me say HSC very frequently, and this is because the LSST pipelines are the Hyper Suprime-Cam pipelines. We've been using, this relationship has been very valuable for both the science community in order to get a preview on what LSST data products are going to look like, and also has been very valuable for us to get a preview of what LSST data, what the sky looks like at 10-year depth. The cameras are very similar, the main difference being that HSC does not have, that HSC has an atmospheric dispersion corrector and LSST does not. This means that image differencing in particular is easier with HSC versus LSST. And so we've been using other precursor data sets for validating that. So in addition to testing the LSST pipelines through these real HSC data releases, we also run a 5 square degree subset of this every month through our continuous integration system. And we have a number of metrics for various performance aspects of the pipeline that we track through time and version number. We do this for both HSC and LSST image simulations donated kindly through Desk's Data Challenge 2. We also run a nightly continuous integration on smaller data sets on both HSC, CFHT, and we run the alert production pipeline on DCAM because there is no atmospheric dispersion corrector and the image differencing performance is closer to what we will see with LSST. Finally, we have the ability to inject fake sources to recover completeness and detection thresholds. So back when this was going to be a real meeting, I was going to introduce you to all the team members so that you know who to ask about what during coffee breaks. In lieu of that, I'm still going to introduce what the team members are working on and give you their Slack handles so that you can ask them questions on Slack instead. Okay. That might be a good pause point for clarification questions before we dig into the details of the pipelines. Okay, oh, sorry. Okay, so this is the roadmap for a data release production. This is going to be our outline, and I'm going to keep returning back to this as we go into each one of these components in more detail. So at a very high level, we take raw images, observatory metadata, calibration data, and reference catalogs as input. We run them through single visit processing, stacking, image differencing, image, coad and difference image processing, and then finally multi-epoch characterization. The boxes at the top are our image data products, our first-class image data products, and the boxes at the bottom are going to be our catalog data products. Some note about our nomenclature for catalog data products. When we say sources and objects, we mean something very, very specific. Sources are the measurements from a single observation. Objects are the measurements utilizing many, typically all observations. These are the logical aggregate. However, note that the objects are not literally aggregates over the sources. They are measured on coads and through light curves and include things like color and are deeper. And I will give you more detail on how both of these components are measured in detail in a bit. So the other jargon here to watch out for is DIA. DIA is just a shorthand for relating to image differencing. Okay, let's talk about single visit processing first. The inputs are the raw images and the outputs are process visit images and sources. Okay, what do I mean by visits? For HSC, this is an HSC focal plane, any exposure on disk can be uniquely specified by a visit number and a CCD number. A visit is one observation of the sky. An exposure is a software object that contains an image, mask, and variance plane, and some metadata, such as a PSF model, a WCS, a photometric calibration, and some visit metadata, such as exposure number, or sorry, exposure time. And these are generally stored as FITS formats. The LSST focal plane is split into refs and sensors. We may change how we refer to these. Instead of visits and CCDs, we might refer to these as exposure IDs and detectors. We will we'll see what patterns shake out. Okay, back to single visit processing. The first stage in single visit processing is instrument signature removal. This is bias subtraction, flat fielding. Robert Lupton will be discussing this component next. The next stage is doing a very preliminary image characterization. So this includes detecting, deblending, measuring sources, estimating a preliminary background, a preliminary PSF, a preliminary WCS, and photometric calibration. The outputs of these are processed visit images, which we affectionately call CALX sometimes, the preliminary version of all of these characterizations, and sources. Sources are useful for calibration and diagnostic purposes, but we do not think they are going to be useful as science data products. For example, for HSC, we don't even release them. If you are interested in light curves, you will rather use the force sources, which I'll tell you about in a bit. And if you're interested in stellar motion, for example, you are interested in the objects. Josh Myers is going to introduce the challenging algorithmic component of PSF estimation later today. So with these sources in hand and process visit images in hand, in the alert production pipeline, we're going to skip straight ahead to difference imaging. In a data release production, we have the time to do some global calibration or Uber calibration. Tomorrow, I'm going to introduce sky backgrounds. Jim Bosch is going to introduce project plans for astrometric calibration, we're using a Megastrom derivative called JointCal, and he's also going to be talking about plans for stellar motion and parallax. And finally, Eli will be discussing the project plans for photometric calibration, including the forward global calibration model or method used by the Dark Energy Survey. So the outputs of this are now finalized background models, WCSs, and photometric calibrations. With those in hand, the next stage is image coaddition and image differencing. The first stage in coaddition is resampling to a common projection. You're going to hear us refer to tracts and patches a lot. These are how we pixelate or tessellate the sky in our COAD projection. It's defined by a software object called a sky map, where you can specify the projection, the pixel scale, the track scale, and the patch size. So on the right-hand side here is an example of a HSC tract. You have, the tract is split into 9 patches in the X direction, 9 patches in the Y direction. They are 4K by 4K pixels wide and high. The red boxes behind is a field of view, is a single visit for comparison purposes. And so our baseline sky map is to use a tan projection in approximately native pixel scale. The track sizes are approximately the size of a focal plane, and the patch sizes are approximately the size of a CCD. The COADs are going to be stored on disk per patch. After resampling onto this common sky map or this common projection, the result is called a direct warp. Direct just means that we haven't done any other convolutions to this image other than resampling, or interpolation or warping. An optional step is to match the PSFs to a common model PSF. Some call this PSF homogenization. The data products from this additional step are called PSF matched warps. These PSF matched warps can be used for a variety of purposes, but right now we only use them for artifact detection. You can compare the warps to find outliers that only appear in a small fraction of images. For example, things like glints or cosmic rays or satellites. But this also includes things like asteroids or supernova. And that's because we want the asteroids and supernova to appear in the difference imaging and not in the COADs, because the COADs, one of the purposes for them is to use them as templates for the statics, templates for difference imaging, and thus they need to be templates of the static sky, a good representation of the static sky. So we'll talk more about artifact rejection later. But this procedure gives us updated masks with which to mask these satellite trails, asteroids, etc., and background offsets. So Jim Bosch is going to be talking about Coaddition later today. He'll go more into the artifact rejection procedure and how we build COADs, but also how we plan to use COADs as templates for image differencing, for deep detection, and spoiler alert, for measurement as well. Okay, so right now, these, so dashed lines mean that it's not what we are doing right now in an HSC data release production, but that is it's an option that you can turn on via config parameters. So right now we use direct coads as templates for difference imaging. We are evaluating using PSF matched coads and DCR coads. So like I said, LSST does not have an atmospheric dispersion corrector, which means that if you observe the same region of the sky at different times of night, depending on the colors of the objects, they will be shifted depending on their color and their air mass. And this is called differential chromatic refraction. And you'll have dipoles appear in your coads with the, with the bright lobe on one side for some objects and the bright lobe on the other side for some other objects. So Ian Sullivan has been working on mitigating the effects of DCR, and will be presenting project efforts towards that later this week on Thursday. So the final stage is using these coads as templates for image differencing, and the final output is difference images. Eric Bellum is presenting this tomorrow, although briefly before I started this talk, I saw a message fly by that he was not feeling well, and this will perhaps be given by somebody else. Okay, the last stage of the processing pipeline is coad and difference image processing and multi-epoch characterization. You'll notice that I said the word processing a lot too. By this, we really just mean detection and measurement. So single visit processing, our software component name for this is process CCD, meaning we detect and measure on a CCD. The process diffim, for example, means we detect and measure on a difference image. Okay, for the coad side of this, we take the coadded images, do detection on all bands, take the union of those detections, and optionally fold in the union of the objects detected on the difference images. And then do blending and measurement, including colors, shapes, and fluxes. With these objects in hand, for light curves, to produce light curves, we can do force photometry on either the process visit images or the difference images, and produce DIA force sources or force sources. We are evaluating the strengths and weaknesses of light curves derived from force photometry on both these types of images. All the tricky algorithmic components here are in this deblending and measurement box. On Thursday, Dan Taranu and Jim Bosch will introduce project plans for galaxy photometry. Jim Bosch will introduce project plans for shape measurement. Colin will introduce project plans for handling all of this in stellar crowded fields, where a lot of our assumptions break down. And starting the pack is a talk from Fred Mulkamp later today about deblending, which was the most highly requested topic for this meeting. Okay, adding on the difference images, my main point here is that difference imaging is not just a stage in alert production. We will also do difference imaging in a data release production as well. The steps here are roughly the same: detection, measurement, and association. That's matching the DIA sources with each other to produce DIA objects. Remember, DIA means difference image analysis. There are a couple of components that will only be used or run in the prompt products or alert production mode. And those are the solar system processing and alert distribution. Both of these topics while, well, very important and interesting, we are not going to discuss later in this meeting because they are not algorithmic components that affect the entire pipeline. Or rather, they are not they are as building blocks, they are not as general as the ones shown at the beginning. Okay, how about you? When we first sent out the Google form for expressions of interest, we asked what aspects of the science pipelines processing are you most interested in? These are the results. And your interests aligned quite well with the aspects that we found challenging as well. So deblending was the most popular. And this asterisk here means that I took some liberties when coding galaxy photometry. Some of you wrote flux measurement or photometry, and if your interests were extragalactic in nature, I took some liberties and coded that as galaxy photometry. Also mentioned were templates, stellar motion, differential chromatic refraction, artifact rejection, coed processing, and brighter fatter. These are going to be folded into one of these talks as well. Okay, so this is what did make the cut for this meeting. What did not make the cut for this meeting? Things like software, data products, science platform, middleware, etc. This is all very interesting, and we think about it daily. But there was a finite time this week, and some of these are going to get a shout out in one of the included talks, and some of them not so much. And so if we don't get to one of your topics later this meeting, please ask on Slack. So what are we doing here? So in the talks that follow, we're going to tell you, why is this algorithmic component important and challenging? What do we do now? What are the current limitations? And we promise we will be honest. And what are the plans for overcoming the limitations? We know you are all in the same line of work, and we are very interested to hear your lessons learned. Did you already try something that we're planning on trying, and did it fail horribly? We want to know. And also think about, will our current plans support your science? And one way to, probably the most useful way to communicate this back to us is through an actual quantitative metric, like a performance metric that we can track through these final years of construction. Okay, I hear my alarm, and this is my last slide anyway. So with that in mind, here's a list of places you can get information, any of our design documents. Please post questions on community or the LSST Slack. You can always look at the documentation and code. And instead of putting a complete glossary, I included a link. Thank you very much.
Thank you very much, Yusra, for that excellent overview and introduction to the LSST Science Pipelines. We have one question currently from Richard Kessler. Richard, I will unmute you when I find you in the list. Just a second. Richard, please go ahead and ask your question.
Okay, maybe too soon for this kind of question, but you mentioned a focal plane solution for the sky. Has this been tested in Mooney conditions? Because in DES, we went from the CCD sky subtraction to full focal plane and had quite some serious issues on Mooney nights. And your focal plane is 3 times bigger.
So the question is, has it been tested on nights with very bright moonlight? Okay, I'm gonna be talking about the full focal plane sky background correction tomorrow. So I would like to defer the discussion of sky background to that talk tomorrow. And I'm really interested in hearing about the problems that you have had.
Richard, would you like to, or Yusra, would you like Richard to go into more detail now, or should we defer this whole discussion to the background talk tomorrow?
I would prefer to discuss backgrounds after the background talk.
Okay.
Because I might answer his question during the talk itself.
That sounds good. Okay, so at this stage, we don't have any more questions on Yusra's talk. So I'd like to thank Yusra again for that introduction to the LSST Science Pipelines.